Hey everybody, Dr. A here, and in this video we're going to be exploring another example of analyzing a stress strain diagram. So let's go ahead and get started. I'm going to go ahead and share my screen, and I'm going to pull up a Word file of another stress strain diagram example. So let's take a look at what we have here. We're being told to refer to the below stress strain diagram that was generated from a tension test and to compute the following. We want to compute the amount of recovered elastic strain if the load on the specimen is increased to 160 KSI and then decreased back to zero. And then part B, we're being asked to compute the permanent set if the load is increased to 160 KSI and then back to zero. So these two parts kind of go hand in hand. So let's go ahead and take a look at the stress strain diagram we have. This is the same diagram that we had in our previous example. So if you watched the previous example, you're looking at the same diagram. On the vertical axis, we have normal stress in kips per square inch. On the horizontal axis, we have normal strain in inches per inch. We have a proportional limit stress of 110 KSI. We have a proportional limit strain of 0.004 inches per inch, or you can just call it dimensionless. Each tick mark or each scale mark on the sigma axis is worth 10 KSI, and you can figure that out by counting the number of scale marks up to 110. You'll find that the 110 KSI value is at the 11th scale mark, which means that each tick mark is worth 10 KSI. And then similarly, each scale mark on the strain axis is worth 0.002. Okay. And so how do we tackle a problem like this? We're talking about loading this. Notice we're loading it beyond the proportional limit value. Okay. So here is how we need to think about this. Okay. We are loading starting at zero. You've got zero stress and zero strain, and you are increasing the load. Okay. So you've got deformation, 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 right? Elastic deformation in this linear elastic region. Then you exceed the proportional limit and you start to get some permanent deformation. Yielding is occurring now, okay? And so we continue to load this up to 160 KSI. So using this diagram, where is the 160 KSI occurring on the diagram? Well, the way I can figure that out is I can say insert and shape, and I'm going to grab a line here. And I'm going to count up to 160 KSI. So here's 120, 130, 140, 150, 160. And I'm going to hit shift and drag a horizontal line over to the right until I intersect the diagram. I'm going to make that kind of a bold orange just so I can see it better. Okay. So what we've done is we have loaded the specimen to a point where we have exceeded the linear elastic region. We have gone beyond the linear elastic region. We have gone beyond the initial yielding region, and this thing has really yielded. Okay, this has got some permanent deformation in it. We know it's permanent deformation because, again, we've gone beyond the proportional limit and definitely beyond yielding. So what does that mean? That means that during a tension test, if you apply load that causes permanent deformation but does not cause failure, notice this, has this thing failed yet? No, failure is all the way out here. Okay, so we've caused permanent deformation, but we have not caused failure. Okay, so what would happen if we turn the tension test machine off? What would happen if we just cut this thing off? Okay, well, what would happen is that specimen would rebound or recover some of its deformation, but not all of it because it has experienced permanent deformation. Okay, so the question becomes how much recovered deformation, or we're going to quantify that using strain, how much recovered strain will we get back? Will the specimen get back? How do we figure that out? Well, what we do is we go to the point of loading, which is this orange dot that I put down here. And I'm going to go to insert. I'm going to insert another line, okay? And I'm going to start at that point, and I'm going to draw a line backwards, okay? Now, what should be the slope of this line? Because you see, I could swing this line around and make it any slope. Well, the slope of this line should be the same slope as the linear elastic region. So here's what I'm going to do. I'm going to draw a line back here, and then I'm going to kind of move it onto the linear elastic region and maybe adjust it a little bit just so it's the correct slope. And then I'm going to move it back here, okay? So I'll use a kind of a bold green just so we can see it pretty well. So what's happening here is we had loading that followed the initial linear elastic region. We exited the linear elastic region. We got to some permanent deformation. We turned off the tension test machine, for example. And what happened was the specimen itself, it rebounded some. It attempted to go back to a portion of its original shape, but because it has had some permanent deformation, it's never going to go back to its full original shape. Okay, hence the name permanent deformation. But what it will do is follow a path back down that would be parallel to the linear elastic region, okay? And that's what this green line represents, okay? So basically what we have essentially done is kind of changed how the material is going to behave moving forward because it now has permanent deformation, all right? And so how do we quantify that? Well, that's what part A is asking us basically, is how do we get the amount of recovered elastic strain? Okay, the recovered elastic strain. So where on this diagram do we think is the representation of recovered elastic strain? Well, what we do is we can insert a vertical line that starts at the point of load application. I'm going to hit shift and drop it all the way down. Okay, so it's going to drop down to about right here. Adjust that just a little bit, about right there. All right. And the recovered elastic strain is going to be the strain that is in between this blue point and this other point on the epsilon axis. I'm going to make that a green point right there, okay? So the recovered elastic strain is the distance between the horizontal distance between this green and blue point, all right? And, you know, I can maybe insert a brace here to kind of help me do that. I'm going to insert this brace and I'm going to rotate it like this just to help me visualize what I'm looking at and stretch it out. So again, these are some tricks of Microsoft Word. Not really tricks, I should probably call it features of Microsoft Word. So that distance right there represents the recovered elastic strain. So the question becomes, what is that distance? Okay, how do I figure that out? Because notice I've drawn a lot of pretty pictures and shapes here, but I haven't actually calculated anything yet. Okay, so the first thing I'm going to be able to do is calculate that recovered elastic strain, epsilon recovered. How do I do that? Well, if I write part A here, okay, I'm going to start with getting the modulus of elasticity, okay? This is going to be the 110 KSI divided by 0.004, and that equals 27,500 KSI. Now, if you want to see a little bit more detail on that particular calculation, see my previous video because I spent more time talking about just that calculation. Okay, so that's the modulus of elasticity. What is that the slope of? Well, that's the slope of this original linear portion, but it's also the slope of this green line, right? So, so I know it's the slope of this green line. So now, because I have the slope of this green line and I have the height of this triangle. Notice I have a triangle here, right? I have a triangle with a green hypotenuse and a blue vertical dimension, and I have this bracket or this brace representing the horizontal dimension. Okay, so how can I set up a slope relationship here? Well, I can say E equals 160 KSI divided by, I'm going to insert an epsilon here, epsilon REC. REC stands for recovered, okay? So again, I know the slope of this green line is E. It's that 27,500. And I know slope is rise over run. So it's the height here, which is 160 KSI, divided by this distance between the green and the blue dot, which is epsilon recovered. Okay, and I just got to do a little bit of rearranging here, and I'm going to copy and paste epsilon recovered, and I'm going to calculate 0.005818 as the recovered strain value. Okay, so again, that's what this distance between the green and the blue dot is. That is epsilon recovered. All right. So if we want to maybe label that, we can say insert shape, and I'm going to use a text box here, and I'm going to say insert symbol epsilon REC. And again, I'm just going to form you. If you watch a lot of my videos, I try to be organized and format things to make it look as professional as possible. You can, on that shape fill, you can say no fill and no outline. And so then I also love Times New Roman font. So there we go. Okay. So that's part of our answer. That's the recovered strain right there. All right. What about part B? Part B says, what's the permanent set if the load increased, to 160 KSI and then decreased back to 0? So what's the permanent set? So permanent set is the permanent strain. So I'm going to say insert symbol epsilon, and I'm going to say epsilon perm for permanent. Okay. So how do I do that? How do I get the permanent set, and where is the permanent set on this diagram? Well, the permanent set is the strain between the origin, which was 0 strain, and the green dot. Okay, that's permanent strain from origin to the green dot. That's how much it's a measure of permanent deformation. So if I use another brace here, I can kind of resize this brace and position it here. And again, we're learning some features of Word here. Okay. And, I can copy and paste this text box over and call this epsilon perm. Okay. Epsilon perm. All right. So how do I get that? Well, what I need to do is get the total length from the origin to the blue point here, and then subtract epsilon recovered from that. Okay, so I'm gonna do that. Now, what is this blue point right here? Well, you could read this off pretty easily. This is 0.004, this is 0.006, this is 0.008. This would be 0.01, 0.009 would be in the middle. So this is about 0.0085 is this blue dot right here, the strain value of that blue dot. So 0.0085 approximately. And then we're going to say minus epsilon recovered, which is minus 0.005818. Okay. And so if I subtract those two, let's see what we get. 0.0085 minus 0.005818. And I get about 0.0027. Okay. Just to go to a couple sig figs there. Okay. And, if you wanted to include units on both of these, they're both going to have units of inches per inch or unitless. Okay. So including this one, inches per inch. All right. So that concludes this example. Again, we are attempting to show another example of how to determine some properties from a stress strain diagram. And in particular, we were looking at investigating permanent deformation of a material from a stress strain diagram. So hopefully you found this video helpful. If you did, please hit like and subscribe and be on the lookout for other videos similar to this. Thanks for watching.